Our topic is lossless data compression algorithm. Actually, a digital system produces messages or symbols in which we have redundant data that is not required, or without which we can retrieve the data or we can decode the data. For example, if a system is sending a sequence of symbols, the next sequence of symbols, then again next sequence of symbols, many a times what happens, you know what will this signal be and what will this symbol be. Knowing the first symbol, you know what the second and third symbol is. So what happens, we have redundant bits of information, or we shouldn't say information, we have redundant bits or redundant symbols in our what we get from the source. And so removal of this redundant data is the objective of this algorithm, that is lossless data compression algorithm. That is, we compress data. If these two are not required, we just omit it. But we know that the entropy of the source limits this compression. You cannot have below this, you cannot have the number of bits of a symbol below this. The average number of bits of the symbol that is being generated by a discrete source, that cannot be less than this. You have seen the average code word length has to be equal or greater than HS. This is your Shannon's first theorem, source encoding theorem. So having this limiting factor, the objective of lossless data compression algorithm is, first is removal of redundant data from data transmission. Removal of redundant data, what we achieve is, we achieve efficiency in average number of bits per symbol. That is the efficiency that we get from removal of redundant data. What is this? Efficiency. Efficiency of what? Efficiency in the number of average number of bits per symbol. And second important thing that is important is that the signal that we generate, or the sequence of bits that we generate after this algorithm, that should be uniquely decodable. That is, if you encode a sequence of symbols in such a way that you are not able to decode it properly at the receiver end, then it's of no use. So there are two objectives, or there are two criteria to be fulfilled here. First is, you have to remove redundant data so that your average number of bits per symbol is efficient. This approach is efficient. Second is, what encoding you do, that should be uniquely decodable. That is, if you send A from transmitter, you should not receive B. You should receive A only. This is the second objective. So keeping these two objectives in mind, we will learn about lossless data compression algorithm. Now, the first type of data compression algorithm is what is called prefix coding. Prefix coding. Why prefix? Because we put prefix conditions. In a signal, we put prefixes, and the code generated by these can be decoded the moment the symbol is received. If you have this symbol, you transmit it at the receiver end. The moment it is received, the whole same sequence is received, you are able to decode it. That is why they are also called instantaneous code. Okay, so I'll take an example and let you understand how this type of algorithm works. Let's say these are the four symbols being generated by the discrete source S, and these are the probabilities associated with each each symbol. Now we have two codes. Let's say the first code system, we assign 0 to S0, S1 to 1, S2 to 0, 0, S3 to 1, 1. And in the second system, we assign this. What happens at the receiver when if we are using this code number 1, we get 0. We know this is S0. When we get 1, we know S1. But what if we get 0, 0? Your algorithm at the receiver, the moment it will get 0, it will go to S0. It won't go to S2 because you have an algorithm that is not able to recognize whether this 0 is for this one or this 0 is for this one. But now look at this particular code. This is unique. You have 0 or 0, 1 and then 1, 1, 0 and 1, 1, 1. Now we have a unique algorithm to decode this. How? Let me explain. Now how? Let's see. What is called that to decode this, we have an algorithm which is called decision tree. See how. See, your code arrives at this point. Okay. The moment it's 0, it goes to S0. Okay. The next digit, it will see for the next digit. If the next digit is 1, it will slip to this point. See. Okay. Why this was not working? Because I have written a wrong code. This is 1, 0 for this. Now let's see. The moment your prefix is 0, it will send to S0 and then it will have the sequence of codes, whatever message you have. Otherwise, prefix is 1, so it will drop to this point. And here this is decision. These nodes are basically decision making points in the algorithm. That is, here you see whether it is 0 or 1. If it is 0, it sends to this direction. So this is symbol 0. If it is 1, it sends to this direction. So it is 0, it will send to this. But the moment it is 1, it sends to this. And then this point starts taking decision. What is the next bit? Now, if it is 0, so it will send to this direction. So you will have S1 here. And then you can decode the message. Otherwise, if this is 1, 1, it will send to this point. See, 1, 1. So 1, 1 will again come to this point. Now again it is waiting whether this is 0 or 1. If it is 0, it will send to this, that is S2. And if it is 1, it will send to this, which is S3. See, S3, S2, S1, S0. So this code is uniquely decodable by this prefix coding algorithm. Our code is like this, not like this. Because if we start with this, see, if this is 0, it will send to 0. If this is 1, it will send to 1, this point. Now, if this is 0, it will send to this, and 0, there is nothing which is actually determining what the next bit is. But if we use this type of code, what happens? This is decision tree. So this is initial state. Now the signal is 0. Immediately it goes to this is 0. So the system will understand that this is for symbol 0. So if we have attached a message with this particular prefix, that message will go to this point. If we have an array or something, that will be stored there. But if it is 1, it will come to this point, and again it will wait for the next bit. See, this is a decision point, decision node. So 1, it comes to this point. If it is 0, it will go to this side. If it is 1, it comes to this point. Again 0 or 1. If it is 0, it goes to this, 1 to this. So this is how prefix coding works. Coding and decoding. It is uniquely decodable. And we have assigned symbols to this. Okay. And because it is decodable the moment it is received at the receiver point, it is also called instantaneous codes. So this is an instantaneous code. Okay. So this is clear. Now from here we come to a very important concept given which is called craft inequality. What is craft inequality? See, you know what is the code word length. You have learned about it. Now let's say, what is the average code word length for this? You know it is summation pk into lk. that is, this is 1, this is 2, this is 3. So this will be 1 into probability 0.5 plus 2 into probability 0.25 and 3 into 0.125 and again 3 into 0.125. So if you add them, this will be your average code word length. Clear? Now from craft inequality, we have a relation which is very important. I'm rubbing this. Okay. Craft inequality, if we have S as S0, S1, S2 and so on, let's say Sk, and the probability associated with them are P0, P1, Pk, and let Sk, the kth symbol, has code word length of Lk. Okay, then according to craft inequality, it is a mathematical expression. It says if you take 2 to the power minus Lk, summation k equal to 0 to 1, that is, you sorry, not 1, k minus 1, you add all them. For example, we had 4 values there. If you take this value 2 to the power minus Lk, this is less than or equal to 1. So in that question also, if you add them all, that is Lk, first was 1, second was 2, then 3 and 3. So first will be 2 to the power minus 1, second will be 2 to the power minus 2, third will be 2 to the power minus 3 and then again 2 to the power minus 3. So what do we get? 1 by 2 plus 1 by 4, 1 by 8, 2 by 8, that is again 1 by 4, 1 by 4. So this is 1 by 4 plus 1 by 4, that is 1 by 2. So this is 1. So at the most it can be equal to 1. This expression is called craft inequality, and for lossless data compression, this has to be fulfilled. When this value is fulfilled, that is, you have code words that fulfill, summation of all those fulfill this inequality, then only you have lossless data compression. Clear? This is craft inequality. Now the point to be understood is that craft inequality only gives the code word length. It gives some relation between code word length and some mathematical expression that has to be fulfilled if that has to be a data compression algorithm, that if that has to be a compressed data. This is for code word length only. It doesn't means that, or I should put it like this, if for example we saw code 1 and code 2, maybe code 1 also fulfills this, but that is not a code word for prefix coding. But code 2, if it has to be an algorithm or a code for prefix conditioning, then it must satisfy this. If a code word violates this, then it cannot be a code word for data compression. But if a code generated code satisfies this, it does not means it qualifies to be a data compression code. There are other conditions also. So this is a condition that must not be violated, but there are other things also to look when we are designing a code. Okay. So from here, if we can construct a prefix code which the code word length lies between this, average code word length lies between HS plus 1. That is, first theorem was this is first theorem, that average code word length is greater than or equal to HS. But if you have to put a prefix, this has to be like this, that is, average code word length should be less than or at least equal to this. This has to be less than this, because you'll at least add one bit as prefix. So this is the meaning of this, that average code word length is less than or equal to HS plus 1, and while it is greater than this condition is very important. And what in case of extended code, we saw that for extended code, this was equal to NHS. We have seen this. So we can write like this: NHS less than equal to extended code is, see, the code word length is HS, NHS plus 1. Or what you can do, you can write like this: HS less than equal to this by N. This is HS plus 1 by N. So this expression is also very important. And one thing to see from this, if you want to see what if N is very large, what will be the average code word length? This is average code word length in case of extended code. So if N tending to infinity, we can write it like this: limit N tending to infinity, HS plus 1 by N. So what if this is infinity? This is 0, so this is HS. So if N is very large, it is almost equal to the entropy of the source. Okay. Now from here we saw what is prefix coding. Now we'll see one of the most important type of coding, which is called Huffman coding. It is an algorithm which is very important. Let's understand what is Huffman coding.